A very good morning to you. Today we are going to look at lesson number 15 of this course, which is on two topics: A, predictive control of time delay systems, and control of inverse response systems. So we are going to look at two typical kinds of processes, which I would rather say two special kinds of processes which arise in the industry in various contexts, and we are going to see special configurations for controlling these processes. So, as is our practice, we will first look at the instructional objectives for this course, which are: number 1, first of all we need to understand how time delays arise in industrial processes, and then we need to understand what is the effect of this delay and why it generally degrades stability and creates problems. And finally, in the context of time delay, we have to look at least one effective way of controlling it and see what it involves. Similarly, for inverse response processes, we have to first of all know what is inverse response and how it arises, and at least an example, and what kind of problems it causes in control, and then see one method again of inverse response compensation. So, this is what we are setting out to learn today. So, let us first look at the causes of time delay. The main cause of time delay is transportation lag. This is the most common and prevalent type of cause for time delay, because in the industry material has to be transferred from place to place in the course of operation, and material transfer, flow of liquids, movements, these things take time. So there is this is called what is known as transportation lag, and causes the majority of the cases where time delay is seen, especially in process control, chemical process control. The majority of the cases is due to this transportation lag. So, this transportation lag can cause a delay either in a process, because things have to be transported from one end to the other. For example, suppose you have a distillation column. So, if you want to have composition control, and if you give an input, let us say either at the either increase the, let us say, the reboiler heat input, then the effect of that input has to travel, that is which will lead to a temperature change in the material. Then that has to physically travel up and down, that is, the vapor has to travel up and the liquid has to travel down to finally affect composition. So, this essentially involves a delay. Similarly, in the case of an actuator, actuators typically, let us say again, let us take the case of temperature control. Temperature is controlled by sending steam, heated steam around jackets of reactors, let us say one way. So, if you give an input, that is, if you increase the steam flow rate by giving a command in a valve, then that increased steam flow rate that steam must travel and fill the jacket for the transfer to actually take place, right. So, therefore, this transportation lag causes delays both in the process and in the actuator. Similarly, apart from transportation lag, there are situations where delays are caused also in the sensors. For example, sometimes you have, especially in composition control, sometimes you have instruments, analysis instruments called analyzers in the loop. So, they will give you various properties of liquids, percentage of a particular ingredient of the composition, I mean something like a gas chromatograph, and these instruments by their very nature they sometimes involve delays. So, sensors can also involve delays. There is another class of cases where sometimes sensors, for example, nowadays in the industry a lot of camera based sensors are used. Now, camera based sensors involve lot of computing, that is image processing related computation to give the result. So, sometimes these computations involve a certain kind of delay, right. In the typical factory context, it is often not significant, this kind of delay, but in other, especially for electromechanical contexts where you need to control at a high speed, sometimes this delay could prove non-trivial. The third very interesting case where something where a delay may be caused is because there is a human in the loop. Apart from coming a little aside from an industrial example, one of the classic examples of a human in the loop control system is a car. So, a car has a driver who is the controller. So, he gets his feedback from his eyes and he reacts by giving control inputs to the car. For example, if he sees that the brake lights of the car ahead lights up, he sees this and jams the brake. So, because of inherent human reactions, this sometimes involves a certain amount of time called the driver reaction time, and in fact this is what in transportation engineering, this is a factor which will eventually decide what can be allowable or safe velocities of cars and safe distances that they must maintain at that velocity. So, humans in the loop can sometimes also cause delays. Now, what are the effects of time delay? Let me tell you that how time delays cause problems. For example, I'll share with you one example of mine. Have you seen you must have seen some modern bathrooms where there is running hot and cold water supply. So, typically you cannot, at least I have not seen a bathroom where you can set the temperature of the mixed water. What is generally provided is a hot water hot water tap whose knob you can turn and a cold water tap. Now, suppose that you want to take a shower and you want the water at a certain temperature. So, what are you going to do? You are going to set up a control loop. How? You are going to you will probably the safe way of doing things is to turn on the cold water to the maximum and then put your hand in the shower and feel the temperature and then adjust the hot water. In fact, this is what I was doing one day, and after some time I realized, so I put my hand in the cold water, it was too cold for me. So, I started turning the hot water tap. So, I was turning and then suddenly I found that the water is too hot, and then I started turning back and then suddenly I found that the water is too cold. After I was doing this unmindfully, and after 2-3 cycles I took notice of this fact that what is happening, why am I not able to set a particular temperature, but rather always either exceeding on the positive side or on the negative side. And then it suddenly dawned on me that wow, this is a typical case of an oscillating process control loop. And why was it happening? Why was the loop oscillating? The loop was oscillating because there was a delay between my turning the knob and the water actually coming onto my hand, because it had to travel through a pipe. So, here there is a transportation lag. There was no lag in the sensor because compared to that delay, the delay in feeling the temperature was negligible, but coupled with the fact that my controller gain was very high, typical taps which you have in the bathroom are quick opening kind of valve, so that you can by a small turn of the knob you can increase the flow rate very fast. And then I was also impatient in the morning, I had to go somewhere, so I was very quickly moving the knob. So my controller gain was very high and there was a delay in the loop. So in effect what resulted was an unstable process loop which was continuously oscillating. So this is exactly what tends to happen in a process loop if the controller gains are high, that it will tend to oscillate. So now let us analyze this phenomenon a little more technically. So here you have this is the standard process control loop where you have this is the controller, and this is the plant, and this is the delay that I am talking about, and this is a normal process control loop. Okay. So what happened? Let us look at what is the closed loop transfer function. Oh, right. To close this, then. So what is the closed loop transfer function? So the closed loop transfer function is very obvious, that is GGC e to the power minus STD divided by, this is the delay. So let's try to look at this transfer function and understand what is happening. First of all, first thing let us notice that in the steady state, how can you get the DC or steady state transfer function? Just by setting in most cases, not all cases, but in most cases you can get the steady state behavior by setting S is equal to 0. So if we set S is equal to 0 irrespective of the time delay, this transfer function will become GGC by 1 plus GGC. So the steady state transfer function is not affected by delay, right. So this is the message, that in steady state delay has no effect, but as we have just seen that it has an effect, it does have an effect in the transient state, that is when set points are changed or when disturbances occur, it is going to have an adverse effect, and it is during these times that the process may start to oscillate, right. So let us try to, that is what we want to study, try to understand. So let us look at this same transfer function in a slightly different way. So the same transfer function I am now looking at the loop in a different way. This was a transfer function. Initially our transfer function was GGC e to the power minus STD. So now this e to the power minus STD, if I take outside, then this part of the transfer function can be represented by this block. So you see that, so now this closed loop transfer function we can represent in a block diagrammatic form in this manner, that there is a delay which is going to be caused in the response. If you give a step input, there is no way that the output will start moving immediately. There is no way that this output will start moving immediately, and we can't do anything about it. It is the inherent characteristic of the plant. On the other hand, now this plant, apart from the delay, how is this plant different from the delay free plant with which we can do ordinary feedback control? So firstly, it is different in the way that there is a delay caused in the output. Now a delay is a delay which cannot be avoided, but nevertheless this delay is not going to cause any problem in stability. Simply the response will be delayed by an amount TD, which cannot be helped. But it is this delay which is going to cause problem in the stability, because it is going to add to the loop phase, right. This is minus STD, so it is going to add loop phase lag, and it is this that is going to cause the problem. Now you see that how does it cause the problem? So to understand that, let us first notice that in the delay free process this would have been a direct term. So in the delayed process we are going to add additional loop phase delay without adding anything to the loop gain, because the magnitude of this operator is always 1, only there is a phase lag. So having noticed that, so this adds to loop phase lag, and therefore here is a comment which we will see in greater detail, that it reduces gain and phase margin. So how does it reduce gain and phase margin? We will see that. It also says that the gain has to be limited to avoid instability. Obviously, if your gain margin is reduced, then the allowable level of gain becomes lower. So you must use a lower gain. Now whenever we know that whenever we use a lower gain, the problem that comes is that you have a degraded transient response. In some cases, for example, if you are using a proportional controller and if you use a smaller gain, then you are going to get greater steady state error, because in the steady state delay has no effect. But if because of stability reasons one has to use a lesser value of k, then that lesser value of k is going to cause a greater steady state error, which is a degradation in performance. So this is the major problem of time delay, but before that let us see how this gain margin and phase margin is reduced. Imagine that the original plan, or not original plan, that the plan to, suppose the transfer function GGC has a, or rather the transfer function has a Nyquist plot like this. Okay. So in this direction, as we know, omega is increasing. So this is the increasing frequency direction. These are the two axes. This is the real axis, rather this is the imaginary axis, and this is the real GHS axis. Okay. So this is generally what is called the phase crossover frequency. So and it is this frequency. This is, if the gain here is GM, then the gain margin is 1 by GM1. So this is that of the loop without delay. Now if you have a loop with delay, then what happens? What happens is that at every frequency now, and magnitude will remain same, and the phase lag, and there will be a phase lag added. So if you add constant magnitude loci, and suppose at this frequency, so phase lag will be proportional to frequency. So suppose at this frequency this much of phase lag is added. So at this frequency, which is higher, some other phase lag will be added. This phase lag will be added. Here this phase lag is added. Here more phase lag will be added. So in other words, now the plant will follow a different trajectory. So it will follow a trajectory like this. So now let me put a different color so that we can understand this phenomenon. We have to put let's put a green color. So now the new plant with delay flows through the green line. So it has got shifted because of the delay. So now what happens? So now now the phase margin has reduced. Previously what was the phase margin? This was the phase margin. That is the phase at this is called the gain crossover frequency. So, the phase margin was this angle. Now, the phase margin is reduced and it is this angle. So, it is this angle now. Similarly, the gain has increased. So, now the gain margin is reduced. So, this is if GM2 is the gain, then 1 by GM2 is the gain margin. So, that has reduced. So, this is how the system is gradually coming closer and closer to instability, and therefore, the maximum gain that you can use for the plant which is represented by the yellow line, the plant which is represented by the yellow line, this yellow line, and the plant which is represented by the green line, you can use a lower gain, right. So, this is what happens, this is why gain has to be lowered to avoid stability, and that in turn causes problems in the response. So, this is the point that I was trying to make. So, having said that, let us go back to our discussion. So, now what is that we want? What is a, so let me present a hypothetical remedy. That is, it would have been very nice, if this delay is anyway this delay is anyway not possible to remove as such. But if somehow we could take the feedback of the process from this point, then at least the stability part of it would have been like a, this is GC by the way. Then at least the stability part of it, from the stability point of view, the effect of delay I could neutralize, apart from the fact that in the response there will be a delay, that is generally not of too much concern in industrial process control, because they are generally I mean, whatever response you want, it will come a little later, that is not so much of a problem. But what is the problem is the change in the feedback loop. So somehow if I could take a feedback from there, but I cannot take a feedback from there because it is within the, because this point is inside the process and it is not measurable. In fact, it is an intrinsic part of the process, right. So, since this point is not measurable, that is why this solution is hypothetical, because we can't take a feedback, actual feedback. But here comes the so now if we could do it then I could have much more improved margin. I could have improved margins like my old case. So, my margins remains would not degrade, and therefore, I can use high controller gains, and therefore, my responses would be like I can use higher controller gains so that I can improve transient response without worrying about the additional stability constraint imposed by the delay. So, that is the problem. So, then how am I going to do this? So, to do this, let me put a so called realizable version of the remedy. So, now what I am going to do is this. So, you see I am giving the original feedback which I was giving, normal feedback, and apart from that I am giving an additional feedback. So, what is this? Typically speaking, in the ideal setting, y is equal to g into e to the power minus std into u, correct. So, this is g into e to the power minus std into u, and on the other hand now you see that if this is a big if, but if I knew g and td very accurately, then there is no reason why I cannot simulate this transfer function and then feed it by u. See, u I have because it is coming out of the controller. So, I already have it, controller is in my machine only, and if I knew the model, so about getting u there is no problem, but about getting, if I knew g and if I knew this td, these are questions how well you can get them, but suppose for the time being that you have it, then we could put it here, and then you see if I add this and this, what do I get? I get GU. So as if, so what is GU? GU is the signal here, this is GU. So by adding this term I am creating a situation as if I am able to make a virtual feedback here, that is what I wanted, right. So if I do that, then I will be able to use the kind of gains that I can use for the system without delay. So this is the basic principle of Smith predictor control. So what am I trying to do? Why is it called a predictor? Why is it called why this term prediction? Because I am trying to, in effect, I am trying to predict the output. Why? Because this is y, this is the output, and what is this? This is nothing but a future output which will appear here in the measurable form after time td. So since I am trying to recreate that. So in other words, I am trying to predict the output and then give it feedback. That is why it is called the Smith predictor control. Now there are of course several questions as to how you can do it. So the first question is that you require to be able to do it, you require this to be known accurately, and more importantly you require this to be known accurately. You see, it is not so simple to estimate time delays, because time delays are often confused with time constants in the response. They actually generate similar kinds of response, and it is very difficult to differentiate between time delay and time constant. But time delays and time constants differ in a very tangible way. What is that way? That for time constants, for example, suppose you have a transfer function called k by 1 plus s tau. This tau is a time constant. So as far as the phase response is concerned, let's take a white page now. Will it come? So this k by 1 plus s tau, let me choose a different color pen because the background is now white. Let me choose black. So the phase of k by 1 plus s tau is going to be limited to minus 90. So it cannot increase beyond minus 90. This is for k by 1 plus s tau. On the other hand, k e to the power minus s tau will have a phase which is increasing linearly with frequency. So there is no bound. So this means, so for example, this system phase is always less than 90, but this system phase is at some frequency it is going to cross, at some frequency it is going to cross the minus 180 point, which is the critical point for stability. So the question is that so there is always this phase lag, the phase lag of the process with a delay is always going to cross 180. But the question is, what is the gain at that point? So to ensure stability, you have to keep the gain low at that point. That is why you have a limit on the gain. While in this case you do not have any limit on the gain. So what happens? So you see that I mean time constants and time delays are slightly different, and time delays are potentially more risky, but distinguishing them from time constant may not always be so simple. So therefore estimating dead time is difficult, and therefore we must have a conservative design. That is, if we think that we should always design a controller K for a worst case delay, because if the delay is, if we design for a best case delay and if the delay is more, then we might land up with instability, right. So this is another problem, that as such we have to limit the gain, and because of the fact that we cannot estimate the delay accurately, in many cases in our design we would estimate it conservatively and will further limit the gain because of lack of knowledge. There may be another case also, there may be cases where the delay may be varying. You see, the delay is caused by what? Delay is caused by transportation lag. So basically it is a time required for the material to flow at a given distance. Now this flow a given distance, how much time is required, that is the time delay, obviously depends on the flow rate. Now the flow rate depends on what? Flow rate depends generally on the operating condition of the plant, right. So if a reactor is producing something at, let us say, 50% volume, then the flow rate will be half of, generally speaking it will be half of if it is working at 100% load. So the time delay will reduce. So now depending on various operating conditions, the time delay in a process can even vary. Not only first of all it may be difficult to assess, secondly it may also vary. So if you are going to design a single controller for all operating points, then further you have to always make a design which will hold good for the worst delay. So which means that for the best case delay you may get very poor response. So actually these are the problems of time delay systems which is somewhat overcome. Now how are these things overcome here? So here also you have to do here also if this G and this just a moment. So here also if this G, I am sorry, if this G and this TD, this has to be selected as black. So if this G and this TD are not properly known, then the compensation that I am talking about will not take place. It will take place only partially. So here also we have to make a conservative design, but at least the situation is better. There is one more point, very interesting point which I wanted to mention. That is the question is that if we want to calculate GU, then and we are saying that we need G, we are assuming that we know G accurately. So if we want to calculate GU and give feedback, and if we have U and we know G, so then why do we need this feedback at all? Why do we need this? Why can't we just take U and then multiply it by G and then give a feedback? That is most simple. But what do we get then? Then we get what is known as open loop control. There is no feedback. What are the problems of open loop control? That any error in G will directly affect the output Y. Any disturbance here will not get corrected. The biggest advantage of feedback control is that it gives you performance generally irrespective of course you have to know certain things, but small modeling errors do not affect performance. That is the single reason for which feedback control is used. And if you take this feedback away, actually this is not, in presence of modeling errors, this is not G to the power minus STD. So if you want to have the benefit of a delay correction according to a model and then also keep your control performance sensitive to modeling errors as well as disturbances, then you must feedback measurement. So you cannot just multiply it by G and send, because then you are going to be blind to the actual reality. If there is a disturbance, that will not be affected here. So it is for this reason that although under ideal condition it actually turns out to be GU, but in real conditions it will not turn out to be GU, and it will, that is your control loop will not become blind to things such as disturbance, things such as modeling errors delta G here, right. So it is for this reason that you must keep the feedback, and it is for that reason that we have added this term rather than taking GU. So these things must be, these are some certain fundamental principles which must be realized in control.